fruitful behavior. We have the communication with the Boeing and also has collaboration with automotive here. I talked with them. So all the modules, they also demonstrate no one uses nonlinear MPC. Here at GM, they are using linear MPC. They are using MPC logic, but they are not using nonlinear MPC. They are using linear MPC. Linear MPC is another story. It can provide fruitful behavior and legible behavior. But if you directly use this one, all this will be done. It's super complex. So I'm not saying this nonlinear model-based design, nonlinear MPC design is wrong or not good. It depends its application scenario or its application domain. If application is safety critical systems, nearly no one can directly use them. So in our framework, it's too highly nonlinear, too complex. In our framework, we permit to simplify this model to the linear one. So here, that is the linear one. It's pretty easy, right? It's very simple here. You can say we would have 0, 0 identified matrix. So it's pretty easy. So in our design, in these requirements, we are using this linear model-based one. So how this model is obtained? We simplify this nonlinear model, just letting the royal pitch reduce and safely go this model. Many parts can be dropped. So that is one benefit. Our framework permits or allow, we simplify the model-based design to be analyzable, to be a variable linear one. So here you may ask, you simplify the model a lot. So how can you guarantee system performance? Because we have the machine learning part, we have the data driving part. Data driving knows we simplify this a lot. So data driving, when learning stage, when training stage, is also searching a policy that can compensate our dropped nonlinear parts. So that is one point here. The second point is fast and stable training. It's viewed from data driven perspective. So here that is the curve or trajectory. It's a curve and a trajectory when we're training this quarterback robots. So here that is it's blue one. It's very short. It is hours. It's our curve. So you can see it quickly reach the convergence. It's very fast. This dark red part. This curve that is we are using the purely data-driven deep reinforcement learning method. So you can see after this almost 9 million steps, still do not converge yet. So we have a comparison, because CMU, they are using the same test bed with us. So in their paper, they claim their total training step to successfully such a policy, good policy. The total training time step is 1/2 billion steps. In our research, in our framework, one day is 1 million. We tried this 1 million, 1 day, 24 hours, we can finish this training and quickly got a fast training, quickly got a probability in the policy. So that is the second benefit here. So we have finished, I have finished the practitioner of the 2 environment embedding. Now we look at the last one. So last one is physics knowledge enhanced DNA. Because deep reinforcement learning, we have the critical network. His job is to approximate the action value function. He also has the action network. His job is to approximate your action policy part. So the deep neural network is the building block of these 2 networks. So here, I would like to first introduce this literature review paper. I would say, physics here is a very homogeneous research topic. This literature review can give you very excellent overviews of the current topics, the current programs. So there are many, programs here, and also there are many funding opportunities. Not only in SF, the DOE has the funding opportunities, and also the NASA. Many opportunities here. So here I would like to add one point is the physics informed machine learning. Previously, the community that studied this one, that is the physics community, So our team, we are physical engineering team. So because we belong to different communities, our proposed solutions are different. We are facing different limitations. So physics community, their job is how can I define, how can I propose a new deep neural network that can solve very complex, very famous nonlinear PDE equation in physics community. They have a lot such PDE equations. Their job is how can I got the solution, and also this solution satisfy the conditions of this PDE. How can strictly follow the PDE equation. But we belong to physical engineering systems, so our solutions are different. So here, this is our proposed physics knowledge enhanced DNA. So figure B is the architecture of each neural network layer. So you can notice, compared with the existing neural network layer, we have two different components. The first one is in-input augmentation. The second one is neural network editing. Neural network editing includes the link editing as the activation editing. The N editing his job is straightforward because we have some physics relations like the Newton motion law. So the N editing is how his job is embed these relations into the neural network insights. And also, if we can embed the knowledge here, we can avoid many spurious correlations, such that the end-to-end input and output can strictly follow the available physical knowledge we have. So, in our research work, we have these keywords that is partially available physical knowledge. Well, we have this partially. That is very, very critical point with the physics community. Because our system is nonlinear, like we drive vehicles. Your vehicles, its data has the interaction with your internal environments, right? Your flat route, your hill route, your icy route, snow route. In the normal condition, sunny day or windy, it's the internal influence on your system is different. But we do not have the